So we learned about Hess's law and how we can take several different chemical equations where the heat of reaction or the enthalpy is known, and add them together and find the enthalpy for a different equation. Where do these heats of reaction come from? They can be calculated from standard enthalpies of formation. Delta H is the change in enthalpy. So that doesn't talk about an absolute value. It just talks about how did it change. So we can define 0 wherever we want. So we define 0 to be convenient. We do other things this way. We measure changes in altitude. We measure altitude relative to sea level. Why? Because it's convenient, right? It's not convenient to measure the distance you are from the center of the Earth. It's easier to do it from sea level, so we do it that way. So we're going to measure changes in enthalpy relative to the enthalpies of pure elements in their standard states. So that's just what we're going to define as 0. So what is a standard state? It's a defined set of conditions. So if the element is a gas, we're talking about the pure gas at 1 atmosphere of pressure. If it's a liquid or a solid, we're talking about the pure substance in its most stable form at 1 atmosphere of pressure, and the temperature of interest. Usually that's 25 degrees Celsius, approximately room temperature. For a substance in solution, standard state is defined as that substance in solution with a concentration of exactly 1 mole per liter. So those are the definitions of conditions for a standard state. The standard enthalpy change. So here we have the change in enthalpy, delta H, and now we've put this superscript 0, or O. That means it's the standard enthalpy change. And this is the enthalpy change when all the reactants and products are in their standard states, those states that we just described. So that degree sign indicates we're talking about standard states. Standard enthalpy of formation. Now we add an F here for formation. So this is standard enthalpy change, enthalpy of formation. This is the enthalpy change when 1 mole of compound is formed from its constituent elements. The elements would be in their standard state. Since that's the change in enthalpy from the standard states, a pure element in its standard state would have an enthalpy of formation or a heat of formation of 0, because that's what we defined as 0 kilojoules per mole. So where do we get these heats of formation? They're found in tables. Here's a table from chapter 6 in your textbook. There's a larger table in one of the appendices at the back, and there are even more available in the CRC, just like pages and pages and pages of them. And each of these numbers represents a lot of work by chemists, because it's not just one person measuring this stuff. It has to be measured by multiple people. So if we look at this table, here we've got the element bromine. So here's bromine as an atom and bromine as a molecule, a diatomic molecule. Well, what does bromine like to do? Is it one of the 7 diatomic elements? Yes, it is. So Br2 is its most stable form. Bromine happens to be a liquid at room temperature. You can tell that on the periodic table because its element symbol is in blue. It's a liquid. So Br2 liquid has a heat of formation of 0, because that's the standard state for bromine. Bromine atoms have a different heat of formation, because that's not how bromine is normally found. So in order to get bromine atoms in the gas state, there would be an enthalpy change of 111.9 kilojoules per mole. So as we look through this table, anytime you see something with a heat of formation of 0, that's the element in its standard state. Okay. Here, carbon has two different common forms, graphite and diamond. And so graphite is the standard state, and diamond is slightly different. So standard enthalpies of formation, we also call them standard heat of formation for the elements. In their standard states at 0, so that's like being at sea level. So basically we're looking at, well, if we make this compound starting from just elements like they would like to be, just regular elements at room temperature, 1 atmosphere of pressure, how much energy change would be required? For most compounds, the heat of formation is negative, meaning that heat is released when that compound forms. So that would be the equivalent of being below sea level. So let's look at methane. So here's methane, CH4. And to find the standard enthalpy of formation for methane, we need to be able to write this formation reaction. So the formation reaction always makes 1 mole of the compound. And so we will sometimes have fractional coefficients, but this heat of formation is kilojoules per mole of CH4. It needs to be 1 mole of product. And the reactants are going to be the elements in their standard states that are present in that compound. So methane has carbon and hydrogen. The standard state for carbon is solid graphite. The standard state for hydrogen is the diatomic molecule in the gas state. So we put those two together and we balance it so that we end up with 1 mole of the compound. If you're not sure what the standard state is for a given element, you can look in the table, the more extensive table in Appendix 2B, and find out which form of that element has a heat of formation of 0. That would be the standard state. So let's write a heat formation reaction for carbon monoxide. Well, carbon monoxide contains carbon and oxygen, right? And so the reactants are going to be carbon and oxygen. But those elements have to be in their standard states. So there's different forms of solid carbon, but the one in the table with a heat of formation of 0 is graphite. So this is carbon in the solid state, and it's graphite as opposed to being diamond. And oxygen, its standard state is O2, gas. So we have our 2 different reactants here and our product. This is not balanced yet, though. Any questions yet? So we need to balance the equation, but we need to keep the coefficient on our products as 1. So we may need to use some fractions. So we have 1 carbon over here, we need 1 carbon here, that one's fine. We need 1 oxygen over here, but this is O2. So we need half of that. So 1/2 of this. So now we have a balanced equation. The heat of formation, we look it up in the table, minus 110.5 kilojoules per mole. So that's a formation reaction for carbon monoxide. So let's write equations for the formation of sodium chloride and lead nitrate from the elements in their standard states. Include the values of delta H for each equation. Okay, so let's do sodium chloride first. So here we have part A. Oh, yeah. Hang on. Okay, for A. Writing the formation equation for sodium chloride. So the product is sodium chloride, solid, because that's what we're trying to write it for. So the reactants are going to be the different elements that are present. So there's only two here. We've got sodium and we've got chlorine. We need to have these in their standard states. What do you think the standard state for a metal is? Bless you. Solid, liquid, gas? Solid. So the standard state for sodium is sodium in the solid state. It's not a diatomic element or anything funky like that. What's the standard state for chlorine? Is it a diatomic element? Yes, it is. So Cl2. What state is it in at room temperature? The color of the symbol on the periodic chart on the wall. It's a gas, right? Anything that has a red symbol is a gas at room temperature. So Cl2, gas. So some of these things we can kind of reason out. Other things you might need to look in the table. And so now we've got our reactants and our product. We need to balance the equation. But we can't put a coefficient in front of sodium chloride. We need this to have a coefficient of 1. So I need 1 sodium. I've got 1 sodium. I need 1 chlorine, but the chlorines are coming in pairs. So that means I need half of this. So we'll put a fraction there. And that's done. So we're also supposed to include the value of the heat of formation. So delta H, F. So we have to go back to that table. And find sodium chloride. So minus 411.2. This equals minus 411.2, and that's kilojoules per mole. Any questions? Okay, let's do the next one. So here we have B. So this one is lead nitrate. So over here for the product, we're just going to write that formula. So it's PbNO3, 2, solid. So what are the elements present there? Lead, nitrogen, and oxygen. Okay, there's 3 of them. So we're not taking this and splitting it into ions. We're starting with elements. So we've got Pb. What do you suppose the standard state for that is? Solid. All the metals except mercury are going to be solids at room temperature. So we've got lead, and then we've got nitrogen. What's the standard state for nitrogen? It's a gas, and it's N2 because it's one of those diatomic elements, right? And then oxygen, O2 gas. Okay, so those are the standard states for the 3 elements found in lead nitrate. So now we balance it. There's 1 lead over here, and there's 1 lead over there, so that's good. In this unit, there are 2 nitrogen atoms, and in N2 there are 2 nitrogen atoms, so that's okay. How many oxygen atoms in this unit? 6. So I need 6 oxygens, so I'll put a coefficient of 3 in front of oxygen. Okay? For delta HF, the standard heat of formation for this, we have to go look it up. Yeah, I was afraid of that. It's not in the table. So that's why I put this in here. Lead nitrate. Do you see it down there? So this is Appendix B. and it's got 3 columns. And the one we're interested in right now is this first column, delta HF, heat of formation. So minus 451.9. So minus 51.9. Any questions? Okay, so the standard heat of formation is forming a compound from its elements in their standard states. So we go from the elements to the compounds, that's delta HF0. If we take the negative of that, if we change the sign, that would correspond to taking the compound and breaking it apart into its elements. So just like a monetary transaction or a transfer between your checking and savings accounts, you go $10 from checking to savings, it's minus for your checking account. You do the opposite, $10 from your savings to your checking, it's positive. If we go from the elements to the compound, it's whatever's in the table. If we do the opposite and go the compound to the elements, we take that number and we multiply by -1. So we change the sign. So what we can do to calculate this standard heat of reaction is we're doing this in our heads. We're not actually doing these reactions, but what we can do is we can imagine taking the reactant compounds and pulling them apart into their constituent elements, so doing this sort of a reaction, and then taking that product and forming it from those elements that we tore apart. This works because of Hess's law and because this is a state function. All that matters is where you started and where you end up, not how you get there. Thank you. So any reaction can be written as the sum of formation reactions or the reverse of those for the reactants and the products. Because we can do that, we can actually shorten things up significantly and say that standard heat of reaction is going to be the sum of the heats of formation for those different reactions that we're imagining. So we're going to end up with the coefficient of each product times its heat of formation minus the coefficient of each reactant times its heat of formation. The negative sign here is because all of the components in the reactants, we are imagining we're taking those apart, and so we would have to change the sign. The products are being made, and so those would be the regular heats of formation. In case you've forgotten this, capital Greek sigma means sum, n is representing the coefficients. Because if you made 2 moles of something, it's going to take twice as much energy. Okay, so here's an example. Combustion of methane. So here's our overall reaction. Methane reacting with oxygen, forming carbon dioxide and water. In the table in our book, we can find a heat of formation for methane, for carbon dioxide, and for water. Those are the 3 compounds that are present here. Oxygen is an element in its standard state. So what's the heat of formation for that? 0, right? Element in its standard state, we decided that we were going to call that 0. So we can look all of these up. So what we're imagining is we're starting here with our reactants, and we're going, this isn't going to change, but we're going to take the methane apart into its component elements. So this is the formation equation for CH4, but we're running it backwards. We're saying, well, we're going to take this apart into the component elements. So this change would be positive 74.6 instead of negative. Now we've got just elements: carbon, hydrogen, oxygen. And so we're going to look at forming the CO2. So forming the CO2 is this equation here. The carbon plus oxygen makes CO2, and the heat of formation is minus 393.5. Well, we're forming 1 mole of CO2, and so this is going to be releasing releasing 393.5 kilojoules. And then we look at forming a mole of water from its elements, and here delta H is minus 241. So we've used the carbon and the oxygen to form the CO2, well, some of the oxygen, and we're going to use the hydrogen and the other oxygen to form water, and that's going to release this amount of energy. So even though this is not actually how the reaction occurs, we're imagining taking this and we're taking everything apart into its basic form, and that requires some energy, and then we're putting together the products, and that's going to be releasing energy. We can look all these things up in a table. We don't actually have to draw this diagram here, but it's helpful to see what's going on. So the way we would solve this without doing this whole drawing and writing out all the equations is we're going to take the heats of formation for the products times any coefficient, because here we're making 2 moles of water, and so we're going to get twice the heat of formation of water. So we're going to take the products and subtract the reactants. So CO2, there's 1 of those, and so that's going to release minus 393.5 kilojoules, and 2 moles of water. So we're adding 2 moles times minus 241.8 kilojoules. So that's the amount of energy released by the products. So this is the sum for the products. The reactants we're taking apart. So this isn't being formed, it's being taken apart. And so this equation, it's the same number, but we have to change the sign. So for the reactants, we're going to have well, we're going to subtract these. That's going to take care of our negative sign. So for methane, this is the heat of formation, and then the heat of formation for the oxygen is 0. So overall, the standard enthalpy or heat of reaction for this is going to be minus 393.5 plus 2 times negative 241.8. That's the products minus the reactants. So we need to be careful with our negative signs, because those can cause trouble. So negative 393.5 plus 2 times negative 241.8. And then I'm going to subtract negative 74.6 equals negative 802.5 kilojoules. Yes?
Why did you use the 2 coefficients?
Pardon me?
Why did you use the 2 instead of
Here?
Yeah.
Okay, because we're making 2 moles of water. So we're making 2 moles of water, so that's going to release twice as much energy. So for that reaction here up at the top, standard enthalpy is minus 802.5 kilojoules. And this we could use to calculate how much energy is released when such and such amount of this burns, etc. Any other questions? This is easier than taking a bunch of equations and trying to figure out how to add them together to get the total, to get the reaction you want. Because we didn't have to look at these, bless you, and figure out, oh, well, we need to put 1 backwards and we need to multiply this one by 2 so that when they all add up, they add up to this. That was the Hess's law calculations, and it's important to know how to do that. But this is much easier. We're just taking everything apart into the elements and then putting them all back, and we can just look up all the numbers. Let's do an example. The thermite reaction, very fun, in which powdered aluminum reacts with iron oxide is highly exothermic. Yeah, it is. You end up with molten iron. So there's the reaction. Use standard enthalpies of formation to find the standard heat of reaction for this. So what we're going to do is we're going to look at this chemical equation, and we're going to say, okay, well, the delta H reaction for this, we're going to have the heats of formation for the products. What would be an easy way? There's no easy way. So this is delta H for the aluminum, and then 2 times the heat of formation for iron. Those are the products, and we're subtracting the sum of the heats of formation for all the reactants. So that's for aluminum and delta H for Fe2O3. So we take our products. If there's a coefficient, we multiply. Heats of formation for those things. And then we subtract all the heats of formation for the reactants. So this is a lot like other delta things, like delta T, where you take the final minus the initial. Here we're taking the final minus the initial. So 2 times the aluminum plus the Fe2O3. Now, before you go looking up heats of formation, are any of these 0? Yes. Which ones are 0? The aluminum, right? So aluminum, that's an element in its standard state. So that's just 0. And what's the other one? The iron. This is also an element in its standard state. So that one's also 0. So that simplifies things a bit. So we need the heat of formation for Al2O3 and Fe2O3. Nope, I didn't put it there. I have to go back. Okay, Al2O3. I'm going to write these on the board because my short-term memory is gone. Minus 1675.7. And Fe2O3 over here, minus 824.2. So we go back over here. So the heat of formation for aluminum oxide was negative 1675.7 kilojoules. We don't need to do the 0. And then we're subtracting the heat of formation for the Fe2O3, 824.2 kilojoules. So negative 1675.7 minus negative 824.2. So we get negative 851.3 kilojoules. Yeah. So for this reaction, the standard heat of reaction, negative 851.3 kilojoules. Any questions? Yeah.
Will it always be final minus initial?
Yes, it's always final minus initial. There's another one. Chemical hand warmers produce heat when they're removed from the airtight plastic wrappers. So here's the heat, the reaction. Iron reacting with oxygen to form Fe2O3. Calculate the standard heat of reaction and calculate how much heat is produced from a hand warmer containing 15 grams of iron powder. So the standard heat of reaction, we're going to take the products minus the reactants, right? So here we have 2 of the iron. So 2 times delta H for the Fe2O3. And that's the only product. Minus the heats of formation for the reactants. 2 times the heat of formation for the iron, plus 3 times the heat of formation for the oxygen. The products minus the reactants. If there's a coefficient, you multiply, because iron would take 4 times as much. Making this would get us 2 times as much energy. Are any of these 0? Why, yes, they are. Both of our reactants are 0. So this is 0, and that one's 0. So it doesn't matter that it's multiplied by 3 or 4, it's still 0. So this ends up being then 2 times the heat of formation for Fe2O3, which thankfully we already have written on the board because we used it in the last reaction, or last problem. So that's going to equal 2 times the heat of formation for Fe2O3. And it's 824.2 kilojoules. So our standard heat of reaction for this is minus 1648.4 kilojoules. Any questions about that? Okay, so that's the first part. Calculate the heat of reaction. Now calculate how much heat is produced from a hand warmer containing 15 grams of iron powder. So this is stoichiometry with energy. We know the mass of iron. 15 grams of iron, there's plenty of oxygen. So we need to take 15 grams of iron, 2 moles of iron, and then this relates to the amounts listed in the equation. So this much energy for every 4 moles of iron that react. So we're going grams of iron to moles of iron to kilojoules. So 15 grams of iron. I'm going to have moles of iron here and grams of iron on the bottom. So the grams cancel out. And then here I'm going to have kilojoules on top and moles of iron on the bottom, so the moles cancel out. Some of you are asking me questions via text message, and I'm really glad you're doing that, and you're showing me your work, which is awesome, because then I can see that some funny things are happening. Make sure that this unit is down there so that they actually cancel out. It's not going to work if I put moles of iron on the bottom and grams on the top. You might want it to work out, but that doesn't make it happen. So make sure your units are actually canceling out. So the kilojoules per mole comes from this heat of reaction. So I didn't leave myself much room. 1648.4, it's a negative, kilojoules, and that is for 4 moles of iron. And then the molar mass for iron, 55.85, yeah. 55.85. It's an element, so we don't even have to do any calculating there. So 15 grams divided by 55.85 to get moles times negative 1648.4. And so I'm getting negative 442.72. This should have three significant figures because of my mass. Kilojoules. Yes? Did I forget that? I did. Yep, thank you. I forgot to divide by 4. It's 110.68. That's why it's always a good idea. You write your answer down, you clear your calculator, you go back and do it again. Because usually you don't make a stupid mistake like that twice in a row, right? You save those for later in the day. Okay, so that would round to minus 111 kilojoules. Now, with energy, we need to be careful of the signs, because sometimes the words tell us the direction and then we don't want to use any negative signs. This is saying how much heat is produced. That tells me that the heat is being released, that overall it's negative. But it's like if I ask you, well, how much did that rock star cost? And you say, negative $3. What, they paid you $3 to take it? No, it costs $3. So here we're not going to put the negative, and we're going to say our answer is 111 kilojoules. That answers the question, how much heat is produced? Now, mastering chemistry, I don't think they're intentionally trying to trick you on this, but you'll feel tricked. I won't try to tease you with this on an exam. But if you come up with a negative number and there isn't that number with a negative in the multiple choice answers, that's why, because it says produced. Any questions?